know Kanchana for a long time.
Wow, yeah. Thanks to Kanchan. Actually, she is the one who contacted you. I asked her, I gave this job to her, said, please find out someone.
Yeah, we have a long association because did her postdoc with whom I also did my postdoc. Of course, we did not overlap that time, but later on we overlapped. Of course, she is much junior to me, but
Yeah, I
we
can
did
see that.
a postdoc.
Now she's our dean faculty.
Yes,
Yeah.
yes. I can see Kanchana now.
Yeah, I can also see
Paul.
Kanchana.
Yeah.
Prempal also we can see. Kanchana, can we start?
Probably she cannot hear you.
Yeah, I don't know who is able to hear us. Somebody must be able to hear us. I think the master of ceremony is a student there.
Maybe you can put a chat message that will be flashed on the screen.
How about now, sir? Hello? Hello? Is it audible? No. You want to say the microphone and left the mic?
It's connected in a different way. What happened?
Nidhi, are you able to hear me?
Yeah, we can.
Okay. The speaker is ready. If you are all ready, we can start.
Yeah, hello.
There's a lot of feedback.
Can you hear us?
I can hear.
Okay, so there is some problem with this connection, I guess. Yeah, so maybe we can start from here, I guess, now. Hello?
Yes, Kanchana.
Okay, so good evening, everyone, and welcome you all to the special evening talk by Prof Murthy. So I welcome you all for the special talk on the occasion of the National Science Day. And to have Prof Murthy among us specially.
Yes.
Sahadas works in the area of computational condensed matter for material physicists, and a major thrust of her research is the application of physical calculations to understand the physics and chemistry of novel and complex materials. She obtained her degree from Calcutta University in 1995. She was a postdoctoral fellow at various prestigious institutes in France, Max Planck, Stuttgart, Germany, and IISc Bangalore. Sahadas Gupta joined SN Bose National Center as a lecturer in 2000. She is currently a senior professor and director of SN Bose. She has so far guided 15 PhD students and published more than 250 research papers. She is a fellow of American Physical Society, the World of Academy of Sciences, Indian National Academy of Sciences, Indian Academy of Sciences, National Academy of Sciences India, and West Bengal Academy of Sciences. She is a recipient of Swarna Jayanti Fellowship, MRSI, ICSE Superconductivity and Material Science Annual Prize, DAE Rajaramanna Prize, Shield Memorial Award, Dr. APJ Kalam HPC Award, and JC Bose Fellowship. She headed the Max Planck India Partner Group, Advanced Material Research Unit, and Thematic Unit of Excellence on computational material science at SN Bose Center. She is a very prolific researcher, and with these few words, I would like to invite her to give the special lecture on the occasion of National Science Day. Professor Tanushree, please.
Thank you so much. Thank you for this kind invitation, and I welcome everyone for this celebration of National Science Day. And I try to share my screen. Is the screen visible?
Yes.
I will make it full screen.
Yes, it is visible.
Okay. So, well, the topic of today's seminar is quantum materials by computation, challenges and opportunities. And as has been already mentioned, I belong to SN Bose National Center for Basic Sciences in Kolkata. This is the institute which was established by Department of Science and Technology to honor the life and work of Professor Satyendranath Bose, in whose name half of the fundamental particles of this world, namely the bosons, are. Okay. So you have heard the term quantum science and technology, and there is a worldwide effort. The all great minds of this world, they have put together a lot of effort in answering the question, how could quantum technologies transform our society? I show some representative example across the world. CIFAR, which is the funding agency in Canada, one of the prime funding agency, you can see that they have put together scientists from different parts of the world, USA, France, Germany, to answer this very question. Institute on Quantum Materials has been set up in the University of British Columbia with the partnership between Max Planck Institute, University of British Columbia, and University of Tokyo, which is a center dedicated on quantum materials. And this is another example of this two-dimensional crystal consortium that has been set up in US, taking into account many different universities of US. And India is not lagging behind in this race, in the sense that India bets big on quantum technology. The quantum technology has been given a massive boost in India's latest budget. In fact, it is now 1 year old news, receiving 80 billion rupees over 5 years as a part of a new national mission that is called Quantum Mission. And of course, in this quantum technology, which is basically the quantum information, the quantum way of communicating from one side to another side, and there have been different platforms that has been discussed for developing such quantum technology, like supercomputing loops, trapped ions, silicon quantum dots, topological qubits, diamond vacancies, etc. and etc. Which one is the right platform, that only future is going to tell us. But there is a big role of materials design behind all of this, because information is physically encoded in materials. So in this quantum technology platform development, the workflow is the following. You start with a theoretical concept for quantum computation, which are like these Marana particles. But once you have such a concept, then for concept realization, you need a system where such a kind of Marana fermions may be found, like topological superconductors, like interfaces between superconductor and ferromagnets, and etc. And the next step, which is very crucial for our talk, is the materials design. That means shortlisting of candidate, which will show such properties like topological superconductivity. And once such a shortlisting is done, the next step is laboratory growth and characterization of these shortlisted candidates. Now, what are quantum materials? Of course, we all know that if we are at 0 Kelvin, at absolute zero, all properties, they are dictated by quantum fluctuation, which is known as 0-point fluctuation. But what we are talking about are the properties which are observed not at 0 Kelvin, but at finite temperature, but still they are governed by the laws of quantum mechanics. So the materials which actually exhibit such properties are known as quantum materials. The examples are superconductors, magnets, topological insulator, multiferroics. The list is long. The properties, the common thing is that all these properties are as a result or manifestation of quantum mechanical effects like quantum fluctuation, quantum entanglement, quantum coherence, the topological behavior. The understanding and prediction on quantum materials, that is basically a multidisciplinary field because that involves the mutual collaboration and handshaking between experiment and theory and simulation, the three vertices of the triangle, because effort has to be put together in terms of synthesis, characterization, design, fabrication, prototype, and important for today's talk is the modeling. So for today's talk, we will focus at the third vertices of this triangle, namely that of the simulation. So the question that is we are trying to answer, can computation create the next wonder material? Well, for these, what we will be doing is basically theory supported by computation. So we hugely, our research depend on the power of the high performance computing. And here I show some representative institute names. This list is by no means it's complete. The list is long. I have just picked a few places which is hosting high performance parallel computing clusters having the peak performance of 100 teraflop or larger. Now, there is also a national supercomputing mission which has a kind of mission to set up petaflop machines. So it's 1000 teraflop will be 1 petaflop. Petaflop machines under this national supercomputing mission across different parts of India. And I'm very happy to share with you that Essenbo Center has been chosen one among the 9 different premier institutes of India where the next supercomputer of 1 petaflop machine will be set up, and these news came just 2 days before this National Science Day. Okay, so in this simulation or modeling, there is a key role which is played by the electrons because electrons are the glue that bind atoms together. So the chemical bonds are basically formed by the electrons. So what is the goal of our research group is to calculate the electronic properties in an ab initio or first principles way. So why and what is a first principles approach? That gives a way of calculating the properties of material before it can be tested in time consuming and costly laboratory experiments. As you can easily imagine, that kind of lab experiment limits the material discovery severely. So the whole idea is before it can be tested in lab, can the computation guide this synthesis process? And the advantage of doing a first principles approach is that it retains all chemical and structural information, therefore is the name as first principle, and it additionally provides microscopic understanding. So it's another triangle where given the structure and composition of a material, the calculation of electronic structure basically helps in calculating the physical properties with the information based on the structure and composition. The properties that can be calculated are the following, like the structural stability, whether a material is in a face-centered cubic structure or body-centered cubic structure, since the total energy of a system can be calculated with an enormous accuracy, the structural stability can be predicted by such calculation. One of the biggest output of this calculation are band structure, which is basically the energy dispersion, and that is connected to the optical properties of a material. It can also calculate the phonons, both in harmonic and quasi-harmonic approximation, and therefore can connect to the Helmholtz and gives free energy. Mostly these calculations are zero temperature, but the access to the finite temperature properties can be obtained through ab initio molecular dynamics simulation, which basically unifies quantum mechanics with molecular dynamics in the sense that the mass of the electron is much, much less compared to that of the ions. So therefore, one can have a separation of time scale, like the time scale associated with an electron is much faster compared to that of the time scale associated with the ions. And therefore, these two time scale can be separated out. And based on these approximation, the electronic degrees of freedom, one basically uses the Schrodinger equation based on the quantum mechanical concept to deal with the electronic degrees of freedom, while the much heavier ions, they are dealt classically by solving the Newton's equation of motion. And these two are connected by the Kelvin-Feynman force in the sense that the force exerted on these ions are created by the electrons, and they are connected they are computed in a completely quantum mechanical way. There is also an ability to handle the strong electron-electron correlation effect, which will be important for a partially filled shell of transition metal, for example, and that can be achieved through the technical advancement of density functional theory, namely the so-called first principle approach, supplemented with some Hubbard U addition. This is a bit technical, but those who are interested can always be in touch with with me, and I will be happy to discuss it further. So I am going to basically show you three different categories of the problem, in the sense that how such a first principle study can help you in addressing these three different classes of problem. The first class of problem is understanding materials property, understanding the structure property relation. Given the structure of a material, how its properties are influenced. And I'm going to show you two very important examples. Like one is that of the superconductivity. So the superconductivity, which was discovered long back in mercury metal with a superconducting transition temperature of 4.2 Kelvin, which basically shows that below this temperature, the resistivity of this material vanishes. So since then, the question has been, how can we enhance this superconducting TC? Because 4.2 Kelvin is still very low temperature to achieve. And this plot basically shows over the year how this transition temperature has been boosted more and more and more. And one of the, a series of compounds that show rather high superconducting transition temperature, they are known as cuprates. They are so called because they are composed of primarily copper and oxygen. You see all this compound has two components, namely copper and oxygen, which is common between all of them. And then we have some other element like lanthanum, bismuth, thallium, barium, or mercury barium. And the superconducting transition temperature is no longer 4.2 Kelvin, but it's kind of an order of magnitude enhancement from 40 to 90 Kelvin. Of course, the whole idea or the goal is, can we push this temperature to room temperature? Now, these materials show superconductivity upon hole doping. And the temperature doping phase diagram, which is kind of generic between all these compounds, is the following. At zero doping, or the undoped material is an insulator, which is an antiferromagnetic insulator. And by increasing the doping, dome-shaped superconductivity shows up. And the highest point of this dome is the transition temperature at optimal doping. And what is listed here for all these compounds, what is the transition temperature at optimal doping? As you can see, while all of these are copper oxygen base, there is a huge variation of this Tc at optimal doping. From 40 Kelvin for the lanthanum compound, for mercury compound, it is kind of more than doubled to 90 Kelvin. So where does this material dependence come from? And what is shown here is basically the crystal structure of such a compound. The basic unit is that of the copper oxygen plane, where a single copper atom is surrounded by 4 oxygen atoms in the plane. They are all in the same plane. And then you have basically stacking of this plane, which is shown with the pink color. And in between, you have the other doping or insulating layer like lanthanum or mercury, or combination of mercury and barium, or bismuth and barium, such kind of thing. But interesting thing is there are 2 more oxygen which are out of plane. And these oxygens are known as the apical oxygen, which actually our calculation shows the most crucial structural parameter. What is shown here is basically the electronic structure or the band structure of the lanthanum compound and the mercury compound. The zero of the energy is set up at the Fermi level. As you can see that at the Fermi level, at the zero energy, there is a single band that is crossing the Fermi level, which is same between the lanthanum compound and the mercury compound. So for a non-expert, very naively, in these 2 compounds, the band structure is pretty similar. There is a single band that is crossing the Fermi level. But the details of this band structure is quite different, in the sense that if you actually compute the Fermi surface, that means you basically take these momentum vectors where this band crosses this zero energy and make a constant energy plot that is known as Fermi surface, it is quite different between the 2 compounds. This is much more squarish for the lanthanum compound, and this is much more rounded for the mercury compound. Well, so far so good. If you just consider the wave function that is describing this single band crossing the Fermi level, the shape of this wave function between the 2 compounds is also quite different. This wave function, which is this wave function describing this single band crossing the Fermi level, for mercury compound it is much more extended compared to the lanthanum compound. What one can calculate is basically the range of such wave function, and which is basically a dimensionless quantity, and plotting the range of such a wave function to this key structural parameter, which is this distance, copper oxygen plane to the apical oxygen. Excuse me. If you plot that, the range parameter across that structural parameter, you see a kind of trend between lanthanum compound, bismuth compound, thallium, and mercury. And we actually carried out long back in this quite well-cited paper in 2001, where we calculated this range parameter for all known whole doped high TC cuprate. And what we found that this range parameter shows a nice correlation. If you focus on this black colored square, don't bother about the other square. These are much more matter of details. And on the other axis, the y-axis, this is a kind of a semi-empirical plot, because in the y-axis, what is plotted is experimentally measured superconducting transition temperature. And this is the result of our calculation, namely the range parameter. It shows a really nice. So in other words, our calculation tells us If we can make this range parameter large, then we will be able to achieve higher and higher transition temperature, the range parameter being connected to the structural parameter, namely copper oxygen to apical oxygen distance. The next example in this context that I would like to show is that of the low dimensional quantum spin system. These are basically transition metal oxides with a small spin. These are all three-dimensional, but the name low dimensional comes because although these compounds are structurally three-dimensional, their magnetic interactions are highly anisotropic and they are dominated either in one dimension or two dimension. So therefore, the magnetic dimensionality is not 3, either it is 1 or 2. And the name quantum spin comes because the spin associated with these transition metal ions like copper 2 plus, vanadium 4 plus or titanium 3 plus is spin half or spin 1. Since it is a small spin and since it is also a low dimensional material, this actually greatly enhances the role of the quantum fluctuation. And that gives rise to fascinating properties like spin gap state, spin charge separation, quantum criticality, even superconductivity. The difficulty is often the true nature of exchange network. That means which transition metal talks to which transition metal in the crystal structure is not what you naively expect from the crystal structure. So for example, there might be two copper ion which in a crystal structure, they just sit next to each other. But as it looks like, the magnetic interaction between these two closely spaced copper ion may not be very strong. Rather, it can be strong between two copper ions which are sitting at a distant place. So therefore, it calls the need for a microscopic investigation, namely the ab initio investigation, together with the application of many-body method to get to the physical properties. So the method is the following. We start with the density functional theory ab initio calculation. From there, what we do is what is known as low energy modeling, like in the sense what I showed in your previous example, picking up this single band that was crossing the Fermi level, because only the electronic states close to the Fermi level are important. That is called a low energy model. And we have a technique to do that. Add the missing electron-electron correlation effect, which cannot be captured within a first principles theory, get into an effective spin model, and then use a variety of many-body techniques to solve that spin model to get into physical picture. What are the physical pictures in the way in this framework can be calculated is one quantity like magnetic susceptibility, the other quantity like spin wave spectrum. The magnetic susceptibility calculated can be compared with an experimentally measured one. And here I show one example. This is a very funny example where all these vanadium spin, they formed like a circle. The structure was like that. And then people considered different kind of spin model in terms of which vanadium ions are magnetically interacting with each other in this circle. And our calculation basically showed the right model, which shows a very nice comparison between the experimental data, which is shown with the circles, and that with our calculation. Such kind of the spin wave calculated spin wave spectrum can be also compared with the neutron scattering result. So therefore, such kind of first principles tool is an effective tool in uncovering structure property relationship. Well, let us now get a bit more ambition in the sense that can we predict new functionalities in known materials? So far, the example that I have discussed where the material was known, meaning all these cuprate compounds were known, and their functionality, namely the superconductivity, was also known. So we basically connected these two things. We knew the material, we knew the functionality, and ab initio calculation basically helped us in connecting the material to the functionality. It provided some microscopic understanding. Now the next class of problem is we have some known materials. These materials has been synthesized. Through such calculation, can we predict some new functionalities? And since these materials exist, these may guide the experimentalists to look for these new functionalities. And here the example I would like to show you are the metal organic complexes and coordination polymers. So these are these materials which are mostly molecular material where you have a transition metal and which are connected through some organic ligand. And since these are organic ligand, they are quite flappy in the sense that they can be perturbed by external means like temperature, pressure, light irradiation, magnetic field, substrate effect, and etc. And what is the result of that? So what I show is the example where the central transition metal ion is a copper 2+ ion. Now this copper 2+ ion has 6 number of d electron, and this is surrounded by 6 of the nitrogen atom, which is contributed by this organic ligand. And since it has 6 nitrogen atoms surrounding it, the 5 copper D level that gets split into 3-fold degenerate T2G and 2-fold degenerate Tg. Now the 6 iron 2+ D electron can be arranged in a following way. Either they can be all paired up as it's shown here with a spin of 0. It's a diamagnetic object in that case. Or it can be arranged in a way that I take 2 of this green arrow and kind of uplift them to the higher energetic Eg level. In this way, of course, one has to basically spend some energy by flipping this 2 down arrow and making it up arrow and setting it to the higher energy Eg level. But you can see in this way the spin is maximized, which is basically liked by the Hund's rule. Now, so therefore there is a competition between how much energy I need to spend in move these 2 of this down arrow to this up arrow in the Eg level. So that depends on this energy level difference between T2G and Eg. So basically it is a competition between the Hund's exchange and the splitting between T2G and Eg. The Hund's exchange is an atomic property, as we all know, and it cannot be changed externally. But what can be changed is this energy difference between T2G and Eg. And that is exactly what has been done by applying temperature or pressure, because by applying temperature, there is a thermal expansion, and that basically expands this bond length between this iron and the neighboring nitrogen. And by expansion of this bond length, what happens is the splitting between these two energy levels decreases, and therefore the Hund's exchange favors, instead of having this configuration to be stabilized. And as you can well understand, this configuration with paired electrons with s equal to spin equal to 0, it's a low spin configuration, while this configuration is called a high spin configuration with a net spin of 2. So a transition from a diamagnetic ion to a paramagnetic ion just by tuning it bond length by some external means. Now all well and good. This phenomena is known as spin crossover phenomenon. Now this is primarily discussed in the context of a molecule. Now instead of a molecular material, can we think of a polymer where we put one molecule to the next molecule, and in that way we basically make a connection between two transition metal center, and therefore the spin crossover phenomena that happens at one iron site resonates with that at the other neighboring iron site, and the whole phenomenon becomes cooperative. If this whole phenomenon becomes cooperative, then the spin crossover, that is the transition from low spin state to the high spin state, the temperature at which such transition happens actually depends on whether I am at the heating path or cooling path. So that means this spin crossover actually shows up with an associated bistability or the hysteresis effect. In other way, your system remembers whether I'm at the cooling path or the heating path. Depending on that, the same system can show up either in the low spin state or in the high spin state. And the low spin state and high spin state, they basically shows up two different colors of the same material because their associated band gaps are different. And this is actually taken from some experiment which shows basically the same sample, but one in heating path, another in cooling path, and at the same temperature, depending on whether you are at the heating cycle or cooling cycle, the same system at the same temperature shows two very different color. So therefore, this can be used as a memory device. So specifically important in this material, as I have just now mentioned, is the large cooperativity shown at the high spin, low spin transition. And what are the possible candidates? One candidate I already mentioned. These are known as coordination polymers, where instead of isolated molecule, we link this molecule, make them talk to each other very extensively. So therefore, you can have a polymer, and these polymers can be one-dimensional, connected three-dimensional pathway. And these are, of course, a best possible candidate to look for cooperativity. We can also think of some material which in today's literature has become very popular, which are known as hybrid perovskite, where we do have a perovskite architectured material, but at the A side, we put some organic molecule. Also, at the ligand side, some organic molecule can be used. So these materials has been hugely discussed in the context of photovoltaic application, but these materials can be also used for showing cooperativity and therefore making memory devices. And this is these materials, as I have already explained, they are of huge potential application possibility. However, there are challenges for material specific predictive theoretical description for many reasons. One reason is we are dealing with transition metal ions, and therefore there is a strong electron-electron correlation effect in the open D shell of the metal center. The complex geometry of the material, very often the unit cell contains some 300 to 400 atoms. So you have to deal with a really complex and large system. And also the third one, which is very important, one needs to capture the electronic and structural changes under external perturbation like temperature and pressure. And we used a lot the ab initio molecular dynamics to take into account the effect of the temperature, as well as I mentioned, the technological development of density functional theory, plus supplemented Hubbard U correction to deal with the strong correlation effect. And we actually predicted some of these hybrid perovskite to be showing the spin crossover by application of pressure, and not only that, showing rather large hysteresis property. Similarly, in terms of the coordination polymeric compound, we showed also for them the spin crossover properties with some associated hysteresis effect. So both these materials are known, they are available. We made some theoretical prediction that these materials can be explored for possible cooperative spin crossover behavior. So, of course, this now needs to be taken up by the experimentalists, explore whether whatever we theoretically predicted is the case or not. So, therefore, this method helps in designing new functionalities. I'll kind of finish with the very last topic, which is a very, very ambitious goal. I think we are kind of rising the ladder and making our ambition more and more. That's the last most ambitious project, predicting new materials altogether. So far we have discussed where the materials is known, functionalities were known. Then in the next example, the materials are known, but the functionalities we predicted. Now in the last example, I want to show where we attempt to predict the materials altogether, meaning these materials did not exist before, and we are trying to predict them. We need new materials with targeted properties for the advancement of the technology, the quantum technology that I talked about. And here I will focus my attention on magnetic materials. Well, I don't need to tell this audience the enormous technological importance, starting from electromagnets, electric motors, generators, to magnetic storage like tape recorders, hard disks, etc. and etc. The use of magnetic materials in our day-to-day functioning is enormous. And there are some magnetic materials which are technologically even more important. So one are ferromagnetic half metals. We know what are ferromagnets, which has a finite spin polarization. There is a net magnetic moment. But some of them are half metals in the sense that the electrons with a certain spin polarization, they conduct, while the electrons with the opposite spin polarization, they don't conduct. So therefore, there is 100% spin polarization of the carriers. And as you can easily imagine, that actually has a technological advantage, because in addition to charge, now one can also use spin to carry information from one end to another end. So that is a tremendous application to spintronics, spin valve effect, central to the idea of magnetic storage and sensing. In this context, there is also quite a big role of antiferromagnetic metals. What are antiferromagnets? Where the spins at the neighboring magnetic sites, they are oppositely aligned in a regular manner. So this is an example of an antiferromagnet. And they can be used as spinning layer in spin valve device, like some of the devices I have already mentioned. But there is a difficulty that both ferromagnetic half metals and antiferromagnetic metals, they are rare in nature. Most ferromagnets, though they are metals, they are not necessarily half metals. And most antiferromagnets we know in nature, they are insulator, they are not really metals. So therefore, we need new material with these targeted properties. And for that, we have to decide on a search space. So we decided on a search space of double perovskite. We possibly know, many people in this audience possibly know, especially those who are in the field of material science, materials physics, and materials chemistry, you are used with a word called perovskite. So perovskite is a general formula AbO3, where A is a rare earth or alkaline earth metal cation, where B is a transition metal cation and O is oxygen. And you have a kind of a structure of a cube where the A atom sits at the corners of the cube, the B atom sits at the middle of the cube, and the O atoms are at the faces of the cube. That's a structure of an ideal cubic perovskite structure. Now you take that structure and make it doubled so that the formula becomes A2B2O6. So since we have B2 now, instead of one transition metal, we can put two different transition metals, namely B and B prime. And we can even make them ordered in a sense, which is a rock salt ordering of B and B prime cation. Then your formula unit is doubled, your unit cell is doubled in all three directions, and I have a rock salt ordering of B and B prime cation. And these materials are known as double perovskite. So why did we focus on double perovskite? In fact, some of these compounds have been synthesized and they are found to be magnetic, and not only magnetic, with a rather high magnetic transition temperature. So to us, it looked like a good place to search for the new double perovskite compound. And this is a very interesting plot, which is taken from this kind of a review article. What are these plot? Let me explain it a bit. So what they did, they fixed the ion at the A site to either calcium, strontium, barium, or lanthanum. And after fixing that, they have considered all possible combination of B and B prime. B along one axis and B prime along one axis. And what are these green colored boxes? The green colored boxes mean those double perovskites have been made, synthesized, their properties has been measured. What are the, you can see some of this yellow colored thing. So these means these are the compounds, double perovskite compounds. They have been synthesized, but for their synthesis, they need some extreme condition like high pressure or high temperature. There are some violet one. That means these compounds have been made, but instead of a perovskite structure, their crystal structure became something different. There are some red boxes, so for which the BB prime combination has been tried to be synthesized, but the synthesis failed. Okay, there are many white boxes. That is what is of our interest. So these white boxes means those BB prime combination have never been tried to be made. And there are so many white boxes. So lots of possibility yet to be explored. So if I was an experimentalist, I will take one of the white box, I will try in my lab, and maybe I will be unsuccessful. So we thought we can be of help in this context. Can we use machine learning? And this is a famous article from Nature in 2016, which says that some researchers believe machine learning techniques can revolutionize how material science is done. Can one really use machine learning for this purpose? Well, machine learning in a very nutshell, this is nothing but a way of pattern recognition. So the steps of the machine learning is you start with a database construction. That means in our case, it will mean we will make a database of all known double perovskite, okay? And try to kind of characterize them with certain basic features. Well, for example, I'm going to explain in a minute, what are their chemistry, what are their structure, without doing any computation, anything. I just take a double perovskite compound as a data point and characterize it. And then, of course, we need some pre-processing step in terms of some of the data points will be an outlier, will have a very atypical thing and that will be discarded, etc. Some of the features will be related, they also needs to be discarded and etc. And once we do that, this is the machine learning step, which is creation of a model to basically understand this pattern. And once we do that, we feed this machinery to some new composition, new compound, and ask the machinery, if we make this compound, will it be made or not? That is the basic idea. And through that, we basically we considered 412 combinations of B and B prime, fixing calcium, strontium, and barium at the A site. And out of so many combinations, we found 33 compounds, which according to our machine learning prediction, it tells very strongly with confidence if they are made, they can be made in a double perovskite structure. 60 compounds with a moderate level of confidence. For 29, the prediction was unresolved because the level of confidence was close to 50. For 54 compounds, we strongly predicted that if they are attempted to be made, they will not be formed in a double perovskite structure or they will not be formed at all. And not only that, what we did, we basically, since these are the new compounds we are predicting, we predicted their crystal structure through some evolutionary algorithm. which for the sake of time, I will not get into details of that, and that will be also a bit technical. But we also clarified their magnetic and their conducting properties. And what we found, there are several examples of ferromagnetic metal, and we also found one example of this rare antiferromagnetic metal. These are the things which we are looking for, and out of these 33 new compounds, new double perovskite compound, we talked about, we predicted them, they can be made, and with this kind of interesting magnetic and conducting property which we were looking for. So I'm going to end with a comment that material matters, and new materials in design is one of the goals of the modern day material science. It's a playground for the future. I wrote a review article for understanding and prediction of quantum materials via modeling and computation. If any of you got interested by my talk and inspired, you can have a look at this review article. And of course, many of the work that I presented here has been done due to the timeless effort and dedication of many of my PhD students. And as you can find that many of them have left and are doing their postdoc in various places or faculties in various places. And we have been deeply benefited by collaborating with a number of very, very distinguished researchers and scientists all across the globe. Thank you very much for your attention. Should I stop sharing?
Hello, anyone there?
Yes, sir, we are here. Just an auditorium. There is some little bit network issue. Maybe I think that they are facing. So, thank you, madam. So I request our director, Professor Murthy, to say a few words. And sir, please.
It has been very, very exciting talk after a long time. I heard thinking into the future. That's how I would like to put it in a nutshell. And for any material scientist, including me, predicting first of all the properties of new materials itself is an exciting thing. Then predicting new materials is one step further, and this is something that these people are excited to do, and I could see that from Tanushree madam's work. And even not only functional materials, people are now even Tata Steel sitting in Jamshedpur. Once upon a time, if they want to make a new steel with a better strength, they used to take almost about 3 to 4 years to experiment. Typical engineers, we do trial and error kind of methods, and then finally come up with a better steel. And now, thanks to the kind of things that you are talking about, what we call in metallurgy or materials engineering as ICME, integrated computational materials engineering, where the whole multi-scale modeling that people are trying to do, and see if we can talk about a new steel with a better property, and by that somehow reduce the timeline of predicting new materials. Now people say within 6 months or so I can come up with a new material, and where the modeling predicts it, and I do a less number of experiments to just validate a few of them and be able to come up. And now you are talking about taking it further using AI and ML to ensure. I've read that paper that you talked about it. We were all excited about it. A new perovskite material earlier. So this is something which Of course, as you rightly pointed out, this is more of a pattern recognition. So it all needs a large amount of expert data available, and through that you are able to predict. So that is one aspect. Of course, your first principle calculations are more of a fundamental physics based approach, where you can also, but possibly this approach of fundamental physics based would possibly take a longer time than an AI based approach. But we have to see where, ultimately somebody should be able to answer the physics behind the predictions that are coming out of an AML. So I think that is where people like you would be able to contribute significantly and say, because everybody says it's like a black box, the A and ML, and the physics behind that is something which is in the hands of people like you to be able to bring it out. I'm, at least as a material scientist, I'm excited looking at the new, I would say, era that is coming up in front of us, the new era where people are able to come up with new materials. I would like to see also very soon, if I remember right, my PhD days, 88, everybody was excited about superconductors. At sitting at IISc Bangalore, every day we were talking about what is the temperature today. So that was a kind of, like what is like the weather forecast of tomorrow. So that is what was, Professor CNR Rao was at the helm of affairs, and he was the director there at IISc. And every day we were so excited. Is it 98 or is it 100 or is it 120? What is it? And everybody is looking forward to a room temperature superconductor. If this kind of a methodology one day can show us very soon a room temperature superconductor, I think that is something which is going to be amazing, that you can actually see these, the so-called levitated trains or whatever it is, much more easily all around us. And as an engineer, I am excited to see if this can lead to such kind of technologies and such kind of materials which will come up with technologies for making our life much better. And ultimately, any science should slowly lead to a technology which will make your life much better. And I'm sure days are exciting, not only now, but future is much more exciting. And thank you very much, madam, for sharing the all your experience and the excitement to all of us. And I'm sure many students sitting here would be possibly taking up some cue from whatever you have said and be able to move forward and be the inventors and innovators coming up with the new materials. Thank you very much.
Thank you very much, sir.
Thank you so much. Maybe I just would like to add, thank you, Professor Murthy, for summarizing it so well. In fact, in our machine learning work, we not only applied machine learning, but we used our fundamental first principles approach to also explain their properties, whatever is predicted by machine learning.
Wonderful, wonderful.
So just connecting to your thing. But thank you so much for summarizing.
Thank you. Thank you.
So, thank you.
Yeah, the expectations are very high. I'm sure you will all be meeting those. Okay. Thank you.
Thank you.
Yes,
Yeah,
Prem,
Professor
over to
Tanushree,
you.
if you can address or if you can answer any of the questions if the students would like to ask.
Yes, please. If there are, I'll be happy to answer.
Maybe ask them to put it in the chat box, Kanchana.
Yeah, because there is sorry for the technical glitch. So maybe we'll try to.
Best thing is, madam can see the chat box, and
Yes.
if anybody has any questions, they can put it. Maybe one moderator can read out the questions.
They don't have. I can circulate it if there are any questions.
Sir, before they ask any question, just for your information, we have very good number of participants online,
Good.
offline. I think first time after this COVID, I have seen very good number of participants in auditorium, and it was giving the feeling now we have started offline.
Yeah. We have to come back. I think there is.
And all four talks were very interesting from, because we organized four talk, as you know, on all were the famous speaker. And I think it is really very good. Students all participants are very happy. They were stuck in the auditorium. And thank you very much, sir, for just encouraging us to celebrate National Science Day at IITH. So if any questions, so please ask question. Yeah, Dr. Surya, please.
Yeah. So thank you very much, Professor Tanushree, for the nice talk. I have one question on our bistability materials. Like you mentioned, like these materials can be useful for the memory application. Can you give some light on that?
Yes.
Before you start, madam, if you don't mind, I have another meeting now.
No problem.
Starting
No
in 1
problem.
minute.
Please.
I will leave. Thank you very much.
Thank you.
We would love you to come to the campus one day very soon.
Sure.
And we will have much more interaction. Okay.
Sure.
I would request Kanchana to fix up a date after taking consent from you. We would love to have you here.
Sure.
Thank you very much. Thank you. Thank you, Prem. Thank you, Kanchana.
Thank you very much, sir.
Yes, I think the question was about the bistability and the memory device.
Memory device, the reason why I'm asking that question is that they are showing at room temperature.
No, that is, you have asked a very, very important point. So first of all, this kind of hysteresis has been seen in different polymers already. So the challenge here, so if you think of the hysteresis, there are two things that you need for a device application. First is to make the width of the hysteresis really wide. That's the first challenge. And the second challenge, as you were trying to say, the midpoint of this hysteresis, which is called T half, to put this T half at room temperature. Because if you see that most of these materials, the T half is around 80 Kelvin or 100 Kelvin, and the width of the hysteresis is more like 10 Kelvin. For technological importance, you need to enhance both of them. And I didn't have time to show, we really have worked on some bimetallic polymer where this T half is increased to about 30 Kelvin, while this the width of the hysteresis, while the T half is really very close to the room temperature.
So is it like, will you enhance those things by applying the pressure or by increasing the temperature? Like
so these two are two different routes to drive the spin crossover. In the other example, which I didn't had any time to talk, if you are interested, I can send you the reference, where we have used a combined route of temperature and pressure. And through these, we could not only induce spin crossover, but also we could basically tune the magnetic exchange between two different metals from ferro to ferrite. And there we use the combined route of temperature and pressure. So I will send you, I will send that reference to Kanchana, and then Kanchana can pass it on to you.
Sure, ma'am. Thank you very much.
Thank you.
Any other question?
So there are no more questions. I would like to thank Professor Tanushree for the wonderful talk. It was really an overview of materials. And as Professor Murthy told, we would love to have you here in the institute, and we look forward for that.
Thank you. Thank you so much. Thank you
so much. Yeah, bye-bye. Prem?
Yeah, yes.
So I am just logging off.
Just ma'am, just a moment.
Okay.
So just the final formality, I think there may be some more questions because of some time limit. They may not be asking. So finally, it is my privilege to propose vote of thanks on the occasion of the National Science Day celebration at IITH. On behalf of organizing committee and the participants, I would like to give my hearty vote of thanks to our distinguished speaker, Professor Tanushree Dasgupta, for accepting our invitation and for giving an excellent talk that made this seminar very meaningful and interesting. Thank you very much, ma'am. On behalf of the Department of Physics, I express my sincere thanks to our Honorable Director, Professor B.S. Murthy, for his support and encouragement to celebrate National Science Day at IIT Hyderabad. I mention my deepest sense of appreciation and would place on record my hearty thanks to all student volunteers, organizing team led by Dr. Niti, our technical team led by Mr. Raghu, and because of whom we made this event possible. And finally, I express my special thanks to all participants who attended all talks online as well as offline. Thank you very much. Thank you very much, ma'am.
Thank you.
We thank HOD sir and Kanchana ma'am for hosting the session. Now we move on to something lighter, something exciting. I mean, science is exciting, but this is a different sort of exciting that we are going to present now. So right now we hand over the stage to
group photo.
She works a lot. She works a lot with blankets. Okay. I have a balloon for you. Okay. So, are you going to take a group picture? Yeah?
Yeah. Come on. All of you, please come this side. Students, please. All the participants.
Yeah.
Just blank the screen. They're going to turn it off. Just blank for some time. Don't turn it off.
They will already